Well, I'm Peter Rowlands. I'm in the physics department here, a research fellow, and I've done a lot of work in various aspects of theory, and I'm going to talk about one of them tonight. I'm going to talk about something that's of immense current interest, about dark energy. And I've got a particular angle on this, which you may find interesting. This is going to be, in fact, very orthodox in many ways. I'm going to use orthodox physics from the beginning and all the way through, but we can get some very interesting answers by doing that. So we start with the Hubble redshift, identified in 1929, and that's Hubble's original graph, and you can see what a perfect straight line it is. Well, the line's perfectly straight, it's just that the points are not very close to it. However, it is approximately linear, and of course it's been refined ever since and to become much more linear. And what's that linearity? It's between the redshift, which was interpreted as velocity of recession of distant galaxies, and the distance of the galaxies. So a recession v and distance r of the galaxies, and v equals h naught r, where h naught was a constant, now called the Hubble constant. And this was interpreted not as the galaxies moving away, but as an expansion of space itself, and it's still so interpreted. However, much more recently, 1998 in fact, a new factor came into this. It was not a purely linear law. In addition to the velocity of recession, there was also an acceleration aspect. And you can see that it's very, very small, but there's a slight deviation from the straight line in that top graph there. You can see it's just slightly veering away from the straight line. It was a very small measurement, but it's been refined ever since. So that was using type 1a supernova, and that shows an acceleration. So this was discovered in 1998, and it's generally described as completely unexpected. Nobody thought it would happen. It took everybody by surprise, that's what we are told, and it doesn't have any explanation, no obvious one. It's clearly going to be a very important phenomenon for cosmology, and maybe for fundamental physics as well. So we need a few basic definitions. So if we got a scale factor r, some distance value, some length, then the Hubble parameter, this isn't the Hubble constant, it's the Hubble parameter, is defined as the normalized rate of expansion. So that's going to be h equals the velocity r dot over the distance r. So the Hubble constant has units of velocity over distance, and when you actually do the measurements, you measure that as the recessional velocity and the co-moving distance. So that's the Hubble parameter. The difference between that and the Hubble constant is that the Hubble constant is the value for now, whereas the Hubble parameter could change and will change over time, certainly if there's acceleration. The Hubble constant is what the value of that Hubble parameter is now. And this is defined in terms of the Hubble radius as c over rh. So it's a quite simple equation, v equals h naught r equals cr over rh. So this is the only time I will use tensors in this talk. I'm just mentioning that is Einstein's field equations of 1915. In principle, the term on the left is the curvature term, and the term on the right is the energy term, which causes the curvature, energy momentum tensor. And when Einstein had that equation, he was concerned with whether the universe would collapse because of the energy term on the right, causing the collapse, causing so much curvature that the universe would collapse. And he added a constant term, a cosmological constant term, that term with lambda on the bottom equation, to avoid that happening, so to keep the universe in steady state. And that was called the cosmological constant term. Fortunately for us, we don't need to worry about Einstein's field equations, because Friedmann in 1922 solved them for models of the universe that are of interest to us. And he found that there were three such models depending on the universe density, and he used two equations to express these models. I will show the two equations as we use them. We will use both of them. But they're quite simple algebraic equations. So from that tensor analysis, the solution becomes quite a simple equation. And those are the three models. I'm sure you know about these. First of all, if the central diagram there shows a universe collapsing because it's above what's called the critical density. So there's a value of density at which the universe, more dense, it will collapse at some point. If it's less than the critical density, it will expand with an increasing expansion forever, and it will be the opposite to the collapsing universe. On the other hand, if it's got the critical density, it should expand but towards a limiting value. So even though it carries on expanding, that expansion will slow down till it reaches a limiting value. Now, if the universe happens to be at the critical density, then it will be flat or Euclidean. And the curvature parameter this is the first Friedmann equation down below. And you can see it's a very simple equation. You've got 8 pi g rho over 3, which is basically the density term, and the curvature term minus kc squared over r squared, where k is the curvature. So this gives you a value for the Hubble constant and this is assuming that there isn't any cosmological constant. When Friedmann did these solutions, I think Einstein hadn't come up with the idea of the cosmological constant. But that can always be added in later. So it's basically velocity over distance all squared is the Hubble constant squared. So that would be the first Friedmann equation. Now at the present time, the critical density can be defined exactly what it must be if the universe is in a state of critical density. It has to be, very simply, 3 times the h0 squared over 8 pi g. So it is a constant expression with units of density. And the ratio of density to this critical value is known as the omega parameter. So rho over rho critical, if rho is bigger than 1, then we get the collapsing scenario. If it's less than 1, then we get the ever increasing expansion. If it's exactly critical, we get the asymptotic limit. Now the value omega equals 1 has a special significance, because if omega equals 1, then we have a flat or Euclidean universe. There's no curvature at all. And that separates it from a universe with spherical geometry, where omega is greater than 1, or an open universe, that would be a closed universe, and an open universe with hyperbolic geometry, where omega is less than 1. That shouldn't say minus 1, it should say less than 1. Now, we know now, to very close degrees of accuracy, to a very high degree of accuracy, that the universe has omega equals 1. It is at the critical density. And this was established around about the year 2000. And I think the key experiment was called the boomerang experiment. And that established that the critical density was 1. Now that became as a bit of a surprise. Most people thought that the universe was a closed universe. Few people thought that it would be Euclidean and flat, but apparently it is. And it's also probably also infinite, because it's hard to see how you can have a flat universe which it can be confined to a finite size. It also means that our calculations become a lot easier, because we can now take them at the Newtonian limit, and so they become effectively just Newtonian calculations. The only difference between ordinary Newtonian calculations and these is that we incorporate energy into the mass term. We just divide the energy by c squared and incorporate it into the mass term, if there is energy on top of the mass in the universe. So this is the critical density. We've got 3h0 squared over 8 pi g. Then it simply becomes equivalent to 3v squared, if you like, velocity over 8 pi gr squared. And if you just rearrange that equation, you'll find it's just basically the Newtonian equation, gmm equals half mv squared. So it's simply potential energy equals kinetic. But the potential energy includes the energy of the universe as well as the pure inertial mass. So m is the total mass, not the discrete mass, not the invariant mass, the relativistic mass. I don't know what that first word is supposed to mean. The mass density doesn't have to be solid matter, as I've just mentioned. So talk about that. I've still got the curvature term there, but you can ignore it. You've got h squared equals 8 pi g over rho over 3. This can include energy. So if we include energy, say, amounting to amount of pressure, you can define if you've got, say, photons or something. If you've got a lot of photons in the universe, then you can define the equivalent energy by using a pressure term, say 3p, the radiation pressure, and or some other such thing, and you can define the mass as 3p over c squared. So you've effectively got a vacuum energy term. Vacuum isn't quite the quantum mechanical vacuum. Vacuum means just something out there other than the lumps of matter. So this is positive. Notice it's plus 3p and p is positive. So if you've got, say, radiation, then that adds to the mass and just makes it more mass. So you end up with 3p over c squared. 3p because it's in 3 dimensions, and that's the way you add that onto the density term. So the density includes the discrete mass and it includes the energy. So P acts with the density, so rho becomes bigger. We assume again K is 0, because that's what our experiment tells us. If we should include a cosmological constant, however, we've left that out so far, but if we should include that, then we would get a negative pressure term. It wouldn't be a positive one, it would be a negative one. So instead of drawing the universe together as the mass and ordinary vacuum energy would, this would be a negative pressure outwards if it was a cosmological constant. And Einstein introduced that in order to have something outwards so he could keep the universe in a constant state. So this would have major physical consequences because this acts against the density. And again we take k equals 0, so we just have the 8 pi g rho over 3 minus lambda squared over 3. Now this is the term that seems to have been discovered in 1998. People immediately say this is the cosmological constant. It's used for a different purpose to Einstein's. Einstein wanted to keep the universe stable. This is pushing it outwards. It's an outward acceleration in the redshift. Now we can incorporate this into the omega value because this is energy, so it's still got a mass value. It's not pulling the universe together. It's not a force inwards, it's a force outwards. But it's still got an energy equivalent and therefore a mass value. Therefore we can incorporate this into the omega. We all call it omega lambda. This is the dark energy component of the critical value of density, omega. Now originally the values that were first put forward earlier in the 2000s and up till very recently were of the order 71.4 to 74%. That was the value that was accepted for this. And this didn't seem to have any particular meaning. It was just that value and there was no clue as to its origin. But this isn't the value that we have now. And what I'm going to say is that the value we have now does give us a clue as to its origin. I'm going to say that just as omega itself is critical, if it's 1, that's a critical value. I'm going to say omega lambda, that section of it which is dark energy, has a critical value as well, or may have. And if it has that particular value, then it will have a precise physical significance. And if it's got that, then if we find new data, we may find it converging on this value, just as the omega in total converged on the value of 1. The first value was a lot varied from 1, it was plus or minus about 10%. So let's have a look to see what the value now stands at. The most recent data comes from the Planck collaboration, which was published in March 2013. And these are there's different ways of doing it, and these are various ways of doing it. And some of them, you can see this one down here is 0.67, and then most are around 0.68, and perhaps one or two 0.69, but generally about 0.68. I think the top one is considered to be the most significant value, but that they all point in the same direction, and there's quite a bit of variation. And notice that we've only got 68% confidence limits, and this is where your statistics comes in. If we had 95 or 99%, it would be we would be more confident of the exact value. But a 68% confidence limits allows quite a bit of a spread. But roughly speaking, it's about 0.68, and this one value down here is 0.67. Now, because it's round about that, what value could that be close to that might be significant? And I'm going to suggest that it is the exact value 2/3 that might be significant. So we're very close to 2/3 with this. 2/3 is certainly within the experimental limits of any of that set of measurements with 68% confidence limits. So it's very close to 2/3 of the total energy. And all we have to do now is to look at a simple calculation to see why that is particularly interesting, that it could be 2/3. Let's suppose that it is. Let's suppose that the vacuum energy, this dark energy, this energy of the acceleration outwards, is 2/3 of the critical value. Then we can actually calculate what the exact value of vacuum energy would be. It would be h0 squared over 4 pi g instead of 3 over 8 pi g. This would be equivalent to a negative pressure, h0 squared c squared over 4 pi g, minus b, notice here, and the cosmological constant. Now, instead of having the cosmological constant as a separate term, we can simply incorporate it into the mass term as a pressure term, the same as if it had been ordinary energy density. But this time, pushing outwards. Incorporate it into Friedmann's first equation, and again make the curvature 0, and we can bring the lambda into the rho term. Now it says plus 3p, but p is assumed to be negative here. So we've got rho plus 3p over c squared as we had before, but this time the p is negative. That's just a standard operation. There's nothing profound about that. Or into Friedmann's second equation. This time we're using the second equation, and this equation gives us the acceleration of the scale factor over the scale factor, 4 pi g over 3 to rho plus 3p over c squared. And we assume rho is the mass density of a uniform and isotropic Hubble universe, and the mass of the Hubble universe is as just a standard mass term within its radius, within the Hubble radius. And so if that is the case, we can express this as a force per unit mass. We can substitute in for 3p over c squared, the expression we've already found, and we find an expression for force per unit mass, which is the one on the right, 4 over 3 pi g rho minus h0 squared times r. So if we hadn't got any dark energy term, it would be just 4 pi g rho r, Newtonian term. Now if we write the force per unit mass that way, then we clearly know what the acceleration is. Gm over r squared, the Newtonian term, force per unit mass, minus h naught squared r, which is the acceleration outwards for the dark energy term. And we can say, and this is very interesting, that A equals h naught squared r. If dark energy is exactly 2/3 of the critical value, 2/3 of the energy of the universe, then we have this equation down below. A equals h naught squared r, or v squared over the radius. And the interesting thing about that is that the acceleration and the velocity are completely determined by the same quantities. H naught, r, v, whichever, they're determined by the same quantities. We've got acceleration is h naught squared r, and velocity is h naught r. And velocity is, acceleration is h naught times the velocity. In other words, in principle, what we're saying is that if this is the case, then the acceleration and the velocity ought to be the same phenomenon. They ought to be part of the same phenomenon. They're not completely different phenomena. It's not like something, you've got your expansion, whatever you want, and then you've got on top of that, you've got some peculiar thing called dark energy. No, they're part of the same phenomenon. At this one value of omega lambda, it depends only on the Hubble constant and the distance, same as the velocity. And so one would think it might be part of the same phenomenon. And we can actually integrate the acceleration to get the velocity term. Or we can differentiate the velocity term to get the acceleration term. Whichever way around you want to do it. So we get the exact Hubble redshift law if we integrate the acceleration term. We got the acceleration and velocity equations solely from the data. We haven't done any conjecture. We've used Friedmann's equations and then we put in the data and got, assuming that the data is this exact value, and got the acceleration and velocity terms. No modelling, no structure, no assumptions whatsoever. We start off with a critical value universe from Friedmann's equations, and then we simply get an acceleration and a velocity term of exactly the sort that we observe. If we assume that the critical value, that the omega lambda is 2/3. Now, if the data stands as it does now, the equation is certainly valid within the confidence limits that have been expressed. And it's certainly valid to within a factor of simply 1.02, plus or minus 0.02, and better than that really. It's so close to being exactly true that we would have to explain why it isn't true if it isn't. Same as we would have had to explain why the critical density wasn't exactly the critical density if it wasn't. So we're in the same position as we were when we were talking about the critical density. And so future probes should be examining whether it is exactly true. We should put this forward as a test of what's happening. That a future probe should actually look out for this. Maybe we should look in the data now to see if it can be expressed in this way. Maybe you astrophysicists can do this. And I'm saying that, I mentioned earlier the boomerang experiment. The 95% confidence interval for omega was simply between 0.88 and 1.12. And they immediately said, this is evidence for a flat universe. So they were 12%, only 12% either way. They had a lot less good value than we have. And yet they immediately said, this must be a flat universe. And everybody from then on believed it was. And then eventually it converged. But even now, it's not converged that much. It's still only within 1% or 2% of the flat universe value. It's not that exact even now. So omega equals 1 has not been established to better than about 1% even now. And in fact, if anything, it's slightly too high. It's slightly too high We know it must be 1, but it measures slightly too high, about 1.01 plus or minus 0.01. As we can see there. That's from the Planck collaboration as well, that particular data. Now, just as a matter of interest, the form of the dark energy law is interesting. That this doesn't rely totally on this methodology, it's true anyway. So you've got the force of gravity, the bulk, which is 1 over r squared. The force of dark energies that's an attractive force, is a repulsive one proportional to r. Now in physics, these are dual laws. You can replace one by another. There's a transformation for doing it. Standard transformation can transform one to another. In gravitational theory, an elliptical orbit can be done by an inverse square law at one focus, or it can be done by a linear law at the centre. They're dual. And these are the only laws that will produce stable orbits. These are the only ones where you can conserve angular momentum and all the things you need for a stable orbit. This is Newton's Principia. I'll just read a few words from this about that, because this is from the Scholium to Proposition 78, Book 1, the Principia. I have now explained the two principal cases of attractions, to wit, when the centripetal force decreases in a duplicate ratio of the distance, 1 over r squared, or increase in a simple ratio of the distance proportional to r, causing the bodies in both cases to revolve in conic sections, in other words ellipses and such things, and composing spherical bodies whose centripetal forces observe the same law of increase or decrease in the recess from the centre as the forces of the particles themselves do, which is very remarkable. And Chandrasekhar, in his book on the Principia, said that's the only place in the whole book where Newton actually expresses any kind of surprise at these results. What we're saying here is that the key significance of this, A equals h naught squared r, is that the velocity term comes directly from the acceleration. One can derive it directly from the acceleration. So whatever the origin of the acceleration, it's responsible for the velocity. If this is the case, if it's exactly 2/3, there's no other way of describing it. This would certainly have impacts on models of cosmic evolution. Cosmological evolution, I should say. However, it's not the only thing we can do. There's another equation. We can derive another equation from the same starting point as well, which gives us an extra possible angle on this concept. And we don't need any model-dependent hypothesis whatsoever. It's just pure mathematics. So this has just been pure mathematics. We've not assumed any model whatsoever. This is about the inertial properties of matter. Basically, why does F equal ma? Why does mass have dual properties, inertia and gravitation? Why doesn't it just have one of them? And would a body have inertial properties if the rest of the universe wasn't there? This is a question which has exercised people's minds for hundreds of years. Ernst Mach said in 1883 that inertia is caused only by the presence of the rest of the universe. He said that the rest of the universe causes a body to have the mass it has. That is called Mach's principle. And Einstein tried to incorporate it into general relativity. And he didn't actually succeed in incorporating it directly, but it was one of the inspirations of the theory. If one is doing general relativity calculations, then there's a useful way of doing some of the calculations because of the velocity of light aspect that comes into it. And one of the ways of doing this is to suppose that we have, in addition to gravity, we have a kind of magnetic type of force associated with gravity, just as there is a magnetic type of force associated with electrostatics, because of the velocity of light. And because we've got the velocity of light involved, we've also got, this is quite standard procedure. And one could set up equations similar to Maxwell's equations for gravity, and many people have. That's quite a standard exercise. And so one would suppose that any equation in electromagnetism will have a corresponding one in gravitational theory, and that has been found. And things like the The more subtle effects that have been measured in recent years are really what we call gravitomagnetic effects. Frame dragging and that kind of thing. Now, Dennis Sharma is well known as Stephen Hawking's PhD supervisor. Back in 1953, Dennis Sharma said that let's suppose the magnetic component of gravity is responsible for inertia. So we start by writing the equation A equals dv dt. This is what we've already found. And then we follow Sharma and consider how to explain inertia along the lines of Mach's principle using a long-range gravitomagnetic inductive force. So clearly this force is not the standard gravistatic force, it's a sort of one equivalent to the magnetic force, it's equivalent to the inductive force between two masses with relative acceleration, which you could derive from general relativity. So inertia is then a long-range force, and that increases with distance. So the further away the distant galaxies are, the more effect they will have. If one did electromagnetism, one would find there was a force between charges E1 and E2 of that kind. You've got your constant over c squared r E1, E2 sine theta dv by dt. And it depends on the acceleration. This is an acceleration-dependent force. This can be derived from Faraday's law of induction. That's quite a standard result. And we can assume that there's one of exactly similar nature between gravity, an inductive force between masses. And you just change the constant, you have g instead of 1 over 4 pi epsilon naught, you change the charges into masses. And this is what Sharma supposed. And he assumed that isotropy would remove the angular dependence theta. So we could then attribute, if you've got a body of mass m, then you could attribute that as due to the inductive force caused by the totality of masses in the Hubble universe within its event horizon. Because this is a velocity of light dependent force, so it must be within the event horizon. And so within the Hubble radius, the totality of masses inside the Hubble radius would cause our object to have its mass. And therefore, if I go back, what we want to do is that dv by dt, we want to make all this into m1, just the mass of the object, or a constant times m1. So what we want is something like F equals kma, where k is a constant. So if that's the case, then the inertial force on a unit mass due to the entire mass in the universe, we keep the same form of the equation, but we've got unit mass, so m1 becomes 1 and m2 becomes mh, the Hubble mass. So it would then be of that form. So a force on a unit mass would be a constant times dv over dt. Well, when you integrated it. So that's one way you can define a mass, by inertia. And this is what Sharma said you should do. What he didn't do was say you can also define it by gravitation. And we can make the connection via the equivalence principle. So let's suppose that the mass, the Hubble mass, defines a radial field of constant magnitude from the centre of the local coordinate system. And at the same time, we're going to equate the magnitude of this mass to the gravitational field inside the Hubble radius. So in other words, gmh over rh squared. This second value is independent of the local coordinate system, but it defines a unit of gravitational mass. It's a bit like on the surface of the Earth, we can define a unit of mass by measuring the acceleration of free fall. So here we're defining a unit of mass, first by inertia and then by gravitation, inside the same radius. Then we will get that equation if we defined those two sets of masses. We get gmh over c squared r dv dt equals gmh over r h squared. And if you look at that, all you need to do is cancel the gmh's out and shuffle the equation, call dv over dt a. switch the c squared over r to the other side, and you get a equals c squared r over rh squared, which equals h naught squared r. So we've actually got back the equation that we got by assuming that the value was 2/3. We've got exactly the same equation by using Sharma's theory of inertia plus the equivalence principle to relate it to the gravitational force in the same sphere. And we could have got that top equation simply by multiplying it out by GMH on each side. Why 2/3 could be interesting, because we can link the dark energy and the Hubble redshift. That's the first good reason for looking at it. The second good reason is that we have a possible way of looking at the Mach's principle and the connection with inertia. This would also suggest, again, that fundamental laws of physics constrain possible cosmologies. You can't just pluck any cosmology out of the air, or out of whatever they pluck it out of. So if we were to have a universe evolving out of nothing or whatever, it would have to create inertial mass at the same time as its space-time structure. And the creation process would have to create the force that would drive its evolution, if one wants to look at that kind of model. So as I was explaining, that equation there is simply another version of that equation. It's just mathematically the same, there's no difference. It's just that this one has extra physical meaning for us. So it doesn't require the development we used. We could just work it out by multiplication, by pure algebra. And that's the whole beauty of all this, that we've had to use nothing except algebra. We haven't had to use any assumptions or model-dependent theory at all. But the ideas that we mentioned, Mach's principle and so on, are a possible context. But we don't need that context to generate the equation. We could have done it anyway. Now, the important thing is that prior prediction is often reckoned to be what you must do to get a theory accepted. You must make a prior prediction, and it must be found to be true. Well, we have a prior prediction, and it's very prior, a long way prior. Because long ago, I had done myself a calculation in reverse as part of a much larger study. And this was when omega lambda values looked as if they were going to be 74%, not 67%, as I wanted. And these were preceded. This is, for example, it's in here, but this is nothing like the earliest version. And the 2/3 value is here on page 605 in this book, Zero to Infinity. We've got many copies in our library if anybody wants to read. But notice page 605. This is 2007, this book. This book is 1994. And this book has the V equals CR over RU, yeah, that's correct, derived from dV over dt, that's acceleration A, equals C squared R over RU squared. That's the same as we've got. So we've got our acceleration and velocity relation in this book of 1994, page 235 on that. These are both my books. Well, that's not the first version. The first version is a long time before this. But 1994 is certainly before 1998. And 2007 is certainly before 2013. But neither are the first versions of those calculations, nor anything like. There's probably about 15 versions that I've done of this calculation in one form or another. I did it in the reverse order, because I've always believed there was a flat universe before they found it. So never believed in anything else. So I had to assume that. I think prior prediction must count for something. So here we've got possible meaning for the dark energy in both physical and cosmological contexts. So possibly we do have critical value for omega lambda, just as we have one for omega. And the critical value is within the limits of the data that we have. I think that we should be looking to see if future probes will converge on this value, just as they converge on omega equals 1. And as I mentioned earlier, even a value which came very close would take a lot of explaining, because it's so close to a critical value. We can't just brush it aside as, oh, it's only within 0.1% or 0.5%, it can't be right. No, it's got to be right if it's close. And if we maybe looked at the data we already have and put this constraint at 2/3 to see what constraints that would provide for the data, that's a job for an astrophysicist. I'm not an astrophysicist, so that is a job for an astrophysicist, but that's an opportunity for an astrophysicist to do it. And another thing that we could look at is how deviations in the universal isotropy and uniformity would be manifested if we did it. That's another research program that could be done. And okay, I'll leave it with the astrophysicists. Thank you.
If hypothetically it wasn't quite 2/3, very, very close, but not quite 2/3, would that directly say that the acceleration and the velocity have to be independent of one another?
No. I would say that if it wasn't exactly 2/3, that would say something probably about the anisotropy or the anisotropy or something like that. It would actually tell us about isotropy or one of those things. You see, if I take I mention Newton's work again, because this is a good analogy here. So he has a calculation on the shape of the Earth, and he thinks that it's going to be an oblate spheroid, and it's going to be about 1/230th figure of the Earth is 1/230. So it's measured in the 18th century, and it's 1/297. But the reason why it's 1/297 isn't because the calculation is wrong, it's because the calculation assumes, knowing that it's wrong, that the density is uniform, and saying that one must iterate to find out what structure the Earth has that will give us the results that we're going to get. So in a sense, it's a test of universal gravitation in one sense, but also, unless you assume universal gravitation, you can't do the calculation. And you know that the calculation won't match up exactly to the data when they're done, but it will be something like. So it won't be exact. So what I would say is, if it's not exact, it's not because it isn't really exact, it's because some inexactness in our assumptions of isotropy or uniformity or something. That's what my guess would be. There'll be some. I think this is too powerful a constraint not to be true. There's a paper on Archive 2013, which you could look at.
I remember you mentioned during your lecture series.
Yeah, I haven't done it.
Paper, not by you, by people who observed, I think.
Well, that's the Planck collaboration.
No, it was another one.
That's a different issue. Yeah, that's about general relativity.
Yeah, but that was. You used that in a sense to relate.
Yes, I did.
This value.
To relate to the more general theory of which this is part.
Yeah.
Yeah. The more general theory of which that's part. I did that.
Have you actually read anything about this?
No, I haven't. So I'm going to try and look it up in the near future.
That might be interesting since.
Because what that was, it was observation of a binary pulsar with two solar masses.
Yeah, it was slightly too high to be real.
And a very high mass binary pulsar, and with a white dwarf companion, I think it's a period of about 4 hours or something, a very short period. So in other words, very intense gravitational field. And people thought that this ought to start violating the equations of general relativity. And the theory I had was that the equations of general relativity wouldn't be high gravitational fields because that concept was based on a wrong interpretation of what the equations said. And so far, there's been no violation of the equations of general relativity, even in strong gravitational fields, much to the surprise of some experimenters. So that's another prediction of mine.
Oh, I have one more question.
Yeah.
Am I right in saying that, so if omega lambda is 2/3,
Yes.
the equation for acceleration would be h naught squared r?
Yes.
I find it remarkably similar to centripetal acceleration, which is minus omega squared r.
Okay.
And
Yeah.
also, if you think of it, the velocity was h naught r, which would be v equals omega r.
Well,
Does that have any significance?
yes, it does, because my wider theory of this is that basically it is a kind of centrifugal acceleration. So it does have a wider significance in the wider context that I was originally did it in. And that's discussed in this book here. Because that was why it was outwards and not inwards. Because it's inertial forces. Inertial forces, centrifugal, Coriolis. Now, I don't really know whether this will work, but I was interested in looking at Coriolis forces and see as well as this would be a centrifugal force because it would be omega squared r, exactly as that. Yeah, which is very interesting. But you can do quite powerful things with fairly simple mathematics. You don't have to do incredibly complicated stuff to get interesting results. I think you need more imagination than anything else. And there's no esoteric mathematics in this. It's all very simple. But it's the key idea. I always think the qualitative ideas are the most important ones.